So hello, good afternoon, everyone. This is Jitka Špolcová from ETN Global. And again, I have the great pleasure to welcome you to our already 8th episode of our webinar series on R&D activities on sCO2 in Europe, which is organized by ETN Global and in particular our sCO2 working group. For those that do not know us yet, ETN stands for Energy and Turbomachinery Network. And we are an international non-profit membership association and also a strategic platform covering the whole turbomachinery technology value chain. Who was here before us, with us in this webinar series? You probably remember that we had a few sessions in the past on component challenges. We also covered balance of plant topic, and last time we concluded with sCO2 cycles for nuclear power generation. And today we will speak about the Horizon EU project called ISOP, which stands for Innovation in Supercritical CO2 Power Generation Systems. As all the previous sessions, also this session is conceived in collaboration with 9 European R&D projects whose names and logos you can see on the screen. When you receive the presentation, you will be able to click on the logos and learn more about the projects. Before we start, I have quite a few boring topics to share with you. This session is recorded, so you will receive the recording after the session. You might want to share it with your colleagues who can't be here, etc. You probably have noticed that by default you came with your mic and camera off. This is correct. However, this will change at the end of the session when we have the Q&As. So the ban will be lifted and you will be able to switch on your camera and the mic and come to us on the stage. I'm sure that you will have questions. So as always, you have two options essentially. So you can either write your questions in the chat and or in the Q&A chat that is provided. And if your question is very concise, very precise and very short, the speaker might want to reply your question directly in the chat. However, majority of questions will be taken for the end, for the Q&A session. So you can as well keep your questions for the Q&A session at the end. You will need your phones because we have 2 Slido questions. And as I already mentioned, the presentations will be provided, so there is no need to take extensive notes unless you really want to. So this is almost it. I want to present the speakers to you. However, before I do it, I want to disclose a little information about the project, not too much because this is up to my colleagues to do it. But I think it would be quite fair to mention that, that the project is quite special because the main players are young researchers that at the end of the project will receive their PhD title in the sCO2 technology. There are 17. I hope very much that they are here with us in the audience. Some of them are with us on the screen, on the stage, and I'll share their faces at least on the screen in a little bit. They did lots of efforts also with preparation of this session, and you will see definitely quite a few of them during the Q&A session. So here they are. Well, first of all, we have obviously David Sanchez, who is also very young, but he already has his PhD. He's also a professor of University of Seville. And last but not least, he's a project coordinator. He will deliver in a little bit an introduction to this session and also to the project. And then you see 2 young engineers, Giovanni and Mohammed, and then they will moderate the Q&A session. I would like to switch to another slide. Yes. So here you see the 4 speakers that will deliver presentations on the work packages of which they are the leaders. So you see the names of the work packages on the screen. So the first one will be Giacomo Persico from Politecnico di Milano. The second will be Lorenzo Cosi from Hughes. Then we'll have Abdulnaser Sayma from Brunel University in London. And last but definitely not least, Fatima Montemor from Tecnico in Lisbon. So we are almost done with my introduction. But before we jump right to the presentations, I would like you to take your mobiles, because the first Slido, as it's always the case with us, comes before presentations. So I would like you to scan the QR code that is appearing very much hopefully on the screen. And this is the first question. So we would like to know what you think about the following. What area of technology needs the most research? So you have 5 different options. It's a multiple choice. You have only one opportunity to vote. So choose one which you think that needs the most research. And if those answers sound familiar to you, you are very right, because you have just seen them on the previous screen, because they are actually the research topics or the topics of the individual work packages. So we want to know which work package, in your opinion, is the most important for the further research within the project. And if you think it's none of them, then obviously pick the last one, which is others, and then maybe why not at the end of the session we can talk about it in the Q&As why you think so. Well, we have 54 persons that voted, which is quite a high number. I think that percentages are not moving very much. So, David, maybe you can help me to debrief this Slido.
Well, yeah, I certainly can, Jitka, thank you. It's interesting to see that we have 2 of the bars leading with a significant gap ahead of the others. It looks like we still think that we need to develop more efficient or more cost-effective, I don't know, turbo machinery and heat exchanger. And that is interesting because most of the work that we do and most of the research revolves around compressors and turbines and recuperators and the likes. Yeah, system operation was probably to be expected because we still have to test the flexibility and the operability of these systems. It's interesting that system integration is actually part of others. It looks like it is very, very clear to us how we should integrate this system. As that is interesting to me because I don't see many projects working on BOP, balance of plant, and the secondary system that you need, for instance, to go part load and work off design. We might have the opportunity to discuss this later in your Q&A. And then from conversation that I had with colleagues, I keep getting the message that probably materials and durability could be the elephant in the room of supercritical CO2 technology. So that is interesting because on the other hand, materials and manufacturing is actually a cross-cutting topic of research because it is not a topic in itself, but it also impacts turbo machinery, heat exchangers, and of course, how much and how fast you can change load in this system. So it is an interesting result, in my opinion, Jacob.
Great, thank you, David, for this debriefing. Well, you can continue staying with me because your introduction comes right afterwards. But before you start, I still want to continue introducing David, even if I said already a few words. So to give you a little bit more information, even if I'm sure that many of you don't know David very well, he's a mechanical engineer by education and has received his PhD on energy engineering by University of Seville. He's currently professor of energy engineering at the same institution, where he leads a team working on sustainable technologies for power generation and for the water energy nexus. And among other functions that he has, he's also a member of the project board of ETN Global. So David, the floor is yours. I will stop sharing my screen.
That is probably longer than the presentation itself. So can you see my screen now?
Yes.
Okay.
Not in the presentation mode though. Yes, now it's perfect.
Now, good.
Yes.
So, well, thank you very much, everyone, for attending the presentation today. Thank you very much, Giacomo and the ETN, for setting this up. It is a very interesting opportunity for the ISO project. I just frame the project so that you can follow the rest of the presentations and maybe see what each work package is aiming to do within the global structure. Now, before that, I would like to frame the project. It is funded by the Horizon Europe program, which, as you probably know, it is a €100 billion project spanning across 7 years. It is organized in 3 pillars according to technology readiness level. The first one, pillar 1, is excellent science. This project falls within pillar 1. It is what we call a Marie Skłodowska-Curie, a Marie Curie action, which is focused on technology development and also training and education of engineers for the future development of R&D in Europe. Now, the project was funded in 2022. The consortium is comprised of 7 academic organizations working on R&D plus 9 industrial partners coming from most countries in Europe. As you can see in green, we are covering a very large part of the continent as well as the UK. We also have 6 industrial associates, meaning that they support the project, they support training and technology development, but they don't really have a budget to do so. So that is out of interest. 10 countries involved, 4.5 million project funded by Horizon Europe and the United Kingdom as well. And we have 17 research topics, as you will see in a minute. The project, it was originally scheduled as a 4-year project, but it eventually was expanded into 5 years for the reasons that I will share with you. So a little bit more in detail, the consortium is, as I said, comprised of 7 academic organizations: University of Seville leading the consortium, Politecnico de Milano in Italy, University of Stuttgart in Germany, Brunel University in the UK, Technical University in Prague, Czech Republic, Tecnico in Lisbon in Portugal, and Technical University of Vienna in Austria. Then we have 15 industrial organizations and spanning across the entire supply chain. So we have 2 machinery manufacturers like Hughes, Siemens, or Doosan. Also the machinery designers like Salting Way. We have heat exchanger manufacturers like Técnicas Reunidas and 5 FIBS. We have system integrators like Empresarios, Agrupados, ARPO, and Borg. We have companies working on materials and additive manufacturing like CITB or Roswell, for instance, and we also have organizations steering or oversteering the entire supply chain, like, for instance, the ETN hosting us today. So as you can see, we are covering pretty much the entire supply chain. Now, the general structure of the project is it was thought of as a 4-year project. The first year, we employed it just to make sure that we were recruiting the best researchers to carry out the research on the topics that we will mention. We took 1 year to do that. And then the remaining of the project is about carrying out technology development. So each of the researchers will enjoy a 3-year contract to carry out a PhD, 2 years employed by an academic organization. And during that period, they will spend a training period of half a year with one of the industries. And then they will eventually join the industry with a full-time contract. So we make sure that they spend 50% of their time with the industry and 50% of their time with R&D institutions. So they get the best out of both worlds. Now, these 17 PhDs will work organized in 4 different work packages: system integration, 5 researchers, system operation, transit analysis and control, 4 of them component innovation, 5 of them for machinery exchangers, and work package 4 working on materials, manufacturing, corrosion, coatings, and all that stuff. Now, I would like to highlight that it is not just 17 people working in isolation like solo runners developing their PhD. There are economies of scale in ISO, and I understand this is a busy slide, so I'll take a bit of time just to go through it. This is what we call the interaction matrix. That means that if we were to order in columns the different researchers or the different topics as you wish, and in rows the same list of researchers or topics, again, Each time you see a colored cell means that the researcher X is exchanging information with the researcher Y. As you can see here, there are many colored cells, which means that there is a lot of exchange of information between the different researchers working on the project. And of course, at the same time, that means that there is a lot of interaction between the different work packages. So it is not just one guy working on the development of efficient compressors, but at the same time, bearing in mind dynamic performance, material, system integration, and all the different elements that you have to take into account. Supporting that, we have a training program that all the researchers will enjoy. Some of these activities are also open to the public in case you're interested. And eventually, we have an international scientific conference held in Brussels where we will disclose all the information that we produce and all the results that we produce throughout the project. So with that, I'm done. And just as a proof of life, just for you to check that there is actually people behind the project. Here you can see some of the meetings that we held and some of the training activities that have already been completed. So thank you very much, and I really hope you enjoy the rest of the session. Back to you, Jitka.
Thanks, David, for the introduction. I think it's a great foundation for the following presentations. So I will now ask Giacomo to join me on the stage. I'm sure that many of you know Giacomo as well. Well, regardless this, I will introduce him a little bit. He's a professor of fluid machines at Politecnico di Milano. He works on turbomachinery with focus on supercritical CO2, organic Rankine cycle, hydrogen gas turbines, and also wind turbines. And within the European research, he contributes to quite a few European projects, including this one, obviously. He is an author of about 200 publications, about 80 of them appear on international journals. So for the moment, this is it from me. Giacomo, the pleasure is mine.
Yeah, thank you, Jitka. Thank you, everybody, for being here. I hope that you can hear me well and you can see the slide. So then I can start. So we start with the discussion of the work packages of this project, starting, of course, on work package 1, which is about system integration. And I mean, after the first slide, I think my aim is to show that there is a lot of research that is to be done on this topic of system integration, probably trying to explain better what kind of research is done in this framework. The work package 1 has a main objective, which is actually related, following its name, to the integration of power cycle components. The idea is that there is a need to train and perform research, train young researchers and perform research in order to obtain an optimal integration of components into efficient SO2-based energy systems for diverse applications like power generation, that means CSP, waste heat recovery, or also nuclear. Also power generation in combination with carbon capture and sequestration, and also in energy storage systems. This diversity of application triggers diversity in technologies, and this can be exploited in the forms of synergies and sharing of experiences to advance knowledge at first, but also develop methods and models, and to understand similarity and difference between different applications. And in doing that, many models and design tools will be developed, also making use of artificial intelligence that enable the optimal integration of CO2 power system and components. What does it mean? As we will see, in many cases, our young researchers are not simply doing thermodynamic calculations. They are creating models that are simple to be implemented and integrated into the thermodynamic cycle, but reliable in such a way that the overall optimization that is the end of their study is technically relevant and useful. So it is just strongly connected to the components. So challenges that trigger the idea of doing our package or dedicating our package to these topics is associated to the need of these models of components to be properly implemented, not as simple efficiency or effectiveness, but models of the components. And we can think to heat exchangers through machinery or separator units for CCS into the cycle calculation, and also to extend these models to the off-design operation to predict the operation of the system in off-design. Also because then there is a work package that is the second one on the controls and the dynamics. And so this part of a design produces a fundamental background for that. And also, we should remember that we need more reliable models and tools to support the commercial exploitation of SO2 energy systems, and this work package covers also that part. So in this, we have 5 young researchers doing their PhD, working on different topics. We can here see their faces and read their names. The first is Giovanni, which is the first PhD candidate that works on the integration of power system based on directly fired oxy-combustion SO2 power cycles, so in connection with carbon capture and sequestration, that is hosted by, from the academic side, University of Seville, and industrial side, Empresarios Agrupados. Then the second one is Amgad. He works on the market uptake of SO2 power system to enable carbon neutrality by 2050, and he is hosted by University of Seville and ETN. Then the third one is Babras, that works on the integration of the power system based on indirect SO2 power cycle, so closed cycles with pure CO2 as working fluid in supercritical conditions. He works in Czech Technical University in Prague, and his industrial last will be Empresarios Agrupados. The fourth PhD candidate is Shaikhrov, which works on large-scale energy storage based on SO2 system that works at the Tecnico University at Wien and with industrial host Empresarios Agrupados. And the last one is Matthias Junek, that works on the utilization of CO2 mixtures to enhance performance of SO2 power systems, that works at Politecnico di Milano and industrial host and POC Consulting. So a few words about the management of the work package. That what is written here is valid also for most of the other ones. All these projects and the PhD project started by the end of 2023 and the start of 2024. So we have now a snapshot of more or less the first year of research, 1.5 years. So we have still 2 years of research in front of us. So this must be taken into account. In the work package, we have already released the first deliverable about the different system configuration for SO2, which is publicly available, and another one will come later on in 2026 about the market potential of SO2 power generation system. And we have already reached 2 milestones about data related to experiment available and market data that are important for this work package. So I think we can now dive into the topics. There are 5, and there are a lot of things to say about them. I will try to be as fast as possible, but still comprehensible. So the first topic we mentioned is about the directly fired SO2 systems. They are very interesting because they are systems based on oxy-combustion that, as you see in this figure on the right, in which you can see the efficiency available or potentially available, can reach very high efficiency, and also in combination with carbon capture and sequestration. And this makes this kind of cycles very well placed into the path towards transitioning towards a decarbonized energy system scenario. And this makes this technology of high interest, but still not very much researched in Europe. So this is the very first project in Europe that covers this topic. And the topic needs to be covered because the gaps were identified in the fact that there are several layouts of directly fired SO2 cycles documented in literature, but we have found a lack of systematic comparison among them, and we want to fill this gap in this work. And also, from the component point of view, we said in this work package, the integration between the components is important. The most important component in this system is the air separation unit, because this is crucial also for the carbon capture and sequestration. And from this literature emerged some discrepancies in, let's say, their modeling and in this power consumption, and this has an impact on the performance on the system and must be studied. So the research that has been done so far about that, let's say, beside the general literature review, was the first development of a systematic method to compare different power cycles of this kind under certain specific boundary conditions that make the comparison fair. And then this was done setting up a detailed model of the ASU, a separation unit, to be integrated into the cycle calculation to perform a relevant optimization about that. Also, behind that, or beside that, alternatives in the way in which the ASU is integrated into the cycle are studied towards an optimization not only of the condition, but on the whole cycle layout. So you can see here some images about the change in the performance and capabilities of the air separation unit for different conditions, which is important for the cycle. The second topic is instead about the market studies, and it was motivated by the need of a roadmap towards the commercialization of SO2 systems, and especially in combination with the different thermal sources available. It was also clear at the time of the preparation of the project that it was needed a proper identification of relevant business cases for SO2, and in this kind of study, in this PhD study, this can be properly done. This is not simple because gaps exist at first from the point of view of the critical technology and supply chain that can affect the market, say, development of the system, depending on the kind of material that can be selected, and maybe they could be interesting, but are not available, or they are not sufficiently known. But also, beside that, there is also a problem of the evaluation of the integration of the system with the market. So at first, to create relevant business cases, it is important to handle the volatility of the market, and the model often struggles to capture the extreme fluctuation, for example, of electricity prices. And also we need forecasting methods, but we have seen that these forecasting methods are difficult to, let's say, develop in a very reliable way, and especially they tend to be very predicted at the very short time and not so much in the long term. So a lot of research has been done in this period about that to introduce for example, external market indicators like fuel prices or weather condition into the model, employ probabilistic methods in the forecasted system to take into account the uncertainties, and also try to integrate this forecasting tool into the trading tool to predict or determine when it is relevant to buy or sell electricity. Also, it was or it is under investigation the possibility to exploit SO2 system in a secondary market. So you can see on the right some figures in which you see, for example, a case in which you have a comparison between the actual prices and the predicted one. And you see on the left, for the first week, a very good prediction is coming, and the second week, you see errors are arising. And this is the issues that are now studied, try to make it more consistent, the validity of the forecasting method during time. The third topic instead is about the, let's say, integration of the power system based on pure SO2 in closed cycles. And this was, even though it is something already studied in several studies, there is a need to introduce improved models, more reliable models of the critical components like heat exchangers and the axial turbine into the cycle. And in particular, the application that was considered was the cycles for the exploitation of the nuclear energy in arid climates, in which, for example, it is important to monitor very precisely in the very early stages of the design, the critical temperature in the heat exchangers like the gas cooler. So the gaps that were identified in that case was the lack of a standardized framework for the let's say, optimal integration of components for this kind of system, and a limited experimental validation at full system scale in the real scale, but some data will arrive in the next months and years that will be useful for the assessment of the model developed in the study. In the study, the first part was focused on the identification of the most suitable cycle layout for this kind of application, which is the recompressor cycle reported in the figure at the center of the slide. Then an interesting feature is that the cycle are optimized introducing, let's say, a two-dimensional model of the heat exchanger in such a way to make more reliable the final prediction and, let's say, to obtain a more relevant final optimization of the cycle. And you can see here, for example, on the right, images of the temperature trends into the high temperature recuperator of the system. And this overall model, which is quite complicated, is now used to optimize systematically the cycle using artificial intelligence. And you see on the figure on the bottom right, the application of some machine learning techniques to predict the cycle efficiency and the turbine work. The fourth topic is similar to the previous one, so thermodynamic cycles, but in this case, not used for power generation, but for energy storage in the form of Carnot batteries. And in particular, just a reminder, Carnot battery is an energy storage system that converts electrical energy into thermal energy and revert back into electricity in another moment. And it is composed by a combination of direct cycle, which is a discharging cycle, and an inverse cycle, like high temperature heat pump, for the phase of charge. Even though it is possible to conceive this kind of cycle considering different fluids, in the case of SO2, the thermophysical properties of the fluid can be exploited to enhance the round trip efficiency of the system. So it is very interesting to study as a technology. And this has some criticalities, in particular connected to, in this case, the heat exchanger between CO2 and the thermal energy storage system. And the tailored models are needed, for example, to avoid that the pinch point, which is the minimum, the point of minimum temperature difference between the two fluids, is in a certain region within the heat exchanger, which is not optimal. And the research is still in its infancy, even though there are projects in the US and also in Europe working on it, but still in the first part. So it is very interesting to have the opportunity to do research on this topic also in this project. And a lot of work has been done on this kind of topic. The steady state models of the cycle has been already developed, and considering both transcritical and supercritical cycles that have been validated with the data available. And it was also studied the impact of extraction and inclusion of thermal energy into the different part of the cycle, and the way in which this can be used to optimize the overall round trip efficiency. And beside that, a study is also active on the component level, so for the high temperature recuperator, and also for different technology for the thermal energy storage system. The last topic is instead about the power cycles used with not pure CO2, but CO2 with mixtures. This is very interesting for another reason. It is interesting in many situations, for example, for concentrated solar power, to exploit this kind of mixtures, because in hot climate, the high temperature for the minimum temperature of the fluid is limiting the efficiency of the cycles. The use of SO2 mixtures, so blends between CO2 and other fluids like SCO2 or TCl4, can enhance the critical point and increase the efficiency of the cycle. This was a technology considered originally for CSP, but can be extended to other applications like waste heat recovery or even nuclear. The gaps in this case come from the availability of precise thermodynamic data on the mixtures, on the knowledge of the effective mixes of earth, environment, and safety, and the assessment of the design performance of components and cycles working on the mixtures. And this is actually under study. it is interesting to see that if a systematic optimization is done, this brings to a transcritical cycle with a temperature change across the condensation because this is a zeotropic mixture that has advantages in the layout of the cooler here, the heat exchanger for the cooling and the condensing. Then the optimization of the cycle has been done, again implementing a one-dimensional model of the recuperator. And for example, here you can see on the figure on the right, the change in the heat transfer coefficient along the heat exchanger. And this is, you can see the variability of that indicates that also with mixtures, there is a huge change of the thermophysical properties of the fluid when approaching the critical point. So it's something that needs to be investigated. And with this information, it was possible to develop not only optimal cycle, but to study the design of these cycles. And this is ongoing at present. So,
Giacomo, I'm afraid to say that we have to conclude.
Yes.
Sorry about that.
Yes, I know. No, you're right. And so the very final slide is that a lot of research has been done already. And as David was saying, this was not done alone. We have identified several collaborations ongoing within the work package and between the different work packages. It's obvious that within the work package, the topic 2 about the market has a significant interaction with the others about market opportunities and limitation, but also estimation about the CapEx of components. And also we have seen a very potential and nice interaction between the topic 3 and 4 because part of the study is similar. Also very interesting are the interaction between the different work packages, especially between work package 1 and work package 2 that we will see in a minute with Lorenzo. Many cycles are similar, but in work package 1 they are studied steady state, and in work package 2 in dynamics and control, and benchmarking is possible. Also, there is an ongoing interaction between all the topics of work package 1 and work package 3 to share information about heat exchangers and turbomachinery, maps, sizing methods, and so on, and between topic 2 and work package 4 to address the gaps we mentioned about material and supply chain. With that, I leave you saying that ready for publications are ongoing and will be presented in 3 conferences this year, in April at the SU2 European Conference, in June at the Esami Turbo Expo, and in September at the ORC Power System Seminar in Lapparato. Thank you. I'm done.
Thank you very much, Giacomo, for your presentation. Sorry again for interrupting you. As you can see, Giacomo could spend so much more time on this, still talking in very structured and very interesting manners. However, we have very limited time, so I would like to ask Lorenzo from Hughes to join me on the stage. And while he's preparing his presentation, I want to share with you, in case you don't know Lorenzo, that he started his professional journey in steam turbine engineering. And in the last 10 years, he has focused on the development of the axial expanders that are required in the novel energy transition cycles, including directly fired and externally heated supercritical CO2 expanders. Lorenzo is currently leading the steam turbine and axial expanders engineering team in Baker Hughes. He has almost 25 years of experience in turbomachinery engineering, covering proposals, design, manufacturing, field, and service aspects. So I see, Lorenzo, that you are ready for your presentation of work package 2, so the floor is yours. Thank you.
Yeah, do you see my presentation? I should be right.
Yes, we do. Everything is fine.
Great. So with the same objective of being fast in the presentation, because as for Giacomo here, we are trying to summarize the work of many people in a concise way, which is not always obvious, because the work that these people is developing is pretty significant and extended. So these are the 3 pillars around which this work package on operability is built. Essentially, we want to define the operational strategy for both the externally heated and directly fired supercritical CO2 power systems, and we know that we have these cycles in many different configurations. So the idea is really to try to structure and in a consistent way some frame, some template that will allow then the industry and researchers that will work on these cycles to have a reference about how these cycles can be operated and which are the elements that we need to put in the plant design to allow this type of operations. Then the other aspects which goes along with the dynamic of this cycle is understanding how from all the operating conditions, I mean, which are the dynamic behavior of which is the dynamic behavior of the cycles, and how this translates into requirements to the different elements of the cycles, like heat exchanger and turbo machinery, condensers. All these elements will get some requirements in terms of, for example, temperature gradient capability, and depending on the capability of these components, or the design of these components, then some constraints to the dynamic and to the operability of the cycle will be set. So another ambitious objective of this work package is to run this interaction between cycle dynamic and component design capability, and establish some basic rules about what is possible for the components and how these translate into the dynamic of the plant. And then the putting all these aspects together, we want to define the control procedure, the control process for the different, which are optimized for the different operating phases of this cycle, for both the undirected and directly fired power cycle. So the work is very ambitious, and the experience that we have today working on this cycle in the European projects, in the interaction with the plant design, is that this piece of information is something that needs to be built. This is something that is very well defined on the other type of cycles, like combined cycles or steam cycles, for example. But now it's time to define the optimized rules for this type of cycles, and we cannot just take what exists on other cycles and adapt here. So here you see the doctoral researchers which are working on these topics. So Matej and Iti Shamul are working on the definition of operating requirement for the externally heated and directly fired cycles. Leonard is taking care of the dynamic and then the interaction with the component requirements and constraints, and Rim is leading the part on control. So going to what they're doing, so starting with the work on the externally heated power cycle, I think we said already what is the purpose. In terms of gaps, we don't find much in literature, or at least we find just some examples of operational strategies which have been defined on the basis of possible configuration of plant, possible configuration of inventory system, bypass valve in some scenarios. So what we see as a major gap is the lack of a consistent definition of the possible plant layout configuration. I mean, the configuration of the elements which are vital to the operability, and how from these elements and the configuration of these elements, the different operating phase of the cycle can be determined. The work that Matej is doing here is started selecting two different types of externally heated cycle, a transcritical Rankine cycle, which is based on the European project experience of Scarabeus and desalination, and a supercritical Brighton cycle, which is based on the Flex European project experience. And on these two cycles is starting the assessment of the possible the configuration of the plant that will enable all the different operability scenario of these plants. In this moment, he has completed the review of the literature, is assessing the transient response of the transcritical ranking cycle with the blend that we see here, the same that was selected for desalination. And as a next step, we'll also work on the Brighton and on a ranking optimized, on a ranking cycle optimized for the concentrated solar plant. And on as a result of all this simulation, it will define this configuration of the plant to possible configuration of the plant to enable the operability. Then moving to the directly fired power system, we have in a similar situation in terms of gap, and we are addressing the same goals. Here, there is an additional complexity brought by the integration of the air separation unit. And again, in literature, we find some example about how the air separation unit can be integrated with the power conversion cycle, but still are just some examples. We don't find a consistent and structured integration strategy. Also for the directly fired cycles, we find in literature different configuration of the cycles. We find the Allan, the Mathiant, the combined cycle one, the Gratz one. And for all of these, we have found some assessment of the steady state performance made by different entities with different assumptions. But we are not, there are limited information about the off design and all the different requirements necessary for the operability of the plants. So the work that Shamula started has initially focused on selecting one of these cycle because we wanted to focus to a single configuration to avoid spreading the effort on too many different cycles. And in order to make this selection, Shamul made a very consistent and comprehensive comparison of the different directly fired cycles that are existing in literature using consistent assumptions. And on this basis, the Allan cycles has been selected as the most promising in terms of efficiency. And on this basis, now on the Allan cycle, now it started the definition of the operational strategy. Then going to the assessment of the impact of the transit operation on the critical component design and vice versa, the constraint dictated by the components to the operability. This is the work which is being developed by Leonard. And in literature, we find a limited set of information about, as was already mentioned by Giacomo, about for example, the dynamic modeling and off-design modeling of the heat exchanger. We find something about the turbo machine, but it's not so comprehensive. And most important, there's not much about the validation of the off-design and dynamic operation of the components and the system itself. So the approach which is being followed here is that the work is now being focused on a promising cycle which recovers the energy from a gas turbine exhaust, and the dynamic model of the cycle that you see here on the top right picture has already been developed along with a control logic that allows making some simulation. And starting from this cycle, Leonard is working and will be working on the optimized and accurate modeling of the most important components of the plant, like the compressor, the exchanger, and also the turbine, to understand how the dynamic behavior of this cycle then translates into requirements for these components, and how these components can limit the operability of the plant. Then for what concerns the control strategy, here the intent is to develop control philosophy for these different power cycles, and obviously this is again a quite ambitious activity. And with this control model, control philosophies and control systems, then evaluate how the different operability scenario can be controlled by this system. Again, if we look at literature, we don't find much in terms of control philosophy. There's not much of validation, and the potential of the advanced control methodology, which are currently employed in the traditional cycles, is not at all exploited. So the idea that is being brought ahead by RIM is to first of all model the off design of the cycle that you see here, which is a supercritical CO2 Brighton cycle applied to a small modular reactor in terms of a heat source. And on this off design model, then simulate first the traditional control methods, and then also some advanced control strategy, and possibly a combination of the two. This will be the starting point in terms of application of control to an externally heated cycle. Eventually, the plan is also to work on a directly fired cycle to define the control strategy also for this type of cycles. So in terms of publications, and this will be what will be available this year, that will start documenting the work of this research. So also here the publication will go mainly at the European conference that will be in Delft in April, eventually at the ASME Turbo Expo in Memphis, and in September then at the ORC Power System conference. And you see here the publications that are already been accepted and will be available once these conferences are done. And the last publication will be on the Applied Thermal Engineering journal. In terms of collaboration, here obviously there will be a collaboration within the work package. As I just mentioned, the plan is to test the control strategy. For example, the one developed for the small modular reactor cycle will be also tested on the gas turbine exhaust cycle, and eventually on the alarm cycle. Then there is a significant interaction also on the modeling of the components with the components work package, and obviously also with the work package 1, because anyway the cycles, there's already been several exchanges about the definition of the optimal cycle to start this activity. In conclusion, I think we believe there is a significant need of research in this area to build the foundations for the operability and the control of these cycles, which is something that needs to be built. And we believe that this work, and then the training and development of these professional talents in this PhD, and then possibly in the future also working, continuing this research work will help building the knowledge that are necessary to develop the operability for this type of cycles. We have seen, and this is also typical for all these work package in supercritical CO2, that there is an attempt to cover all the different, and there are many options of cycle configuration, so to address all of them and try to provide solutions for operability which are consistent and can be applied to most of these cycles. The other important point is that we just see some results. We'll see just some public result this year, and also important, I think is also important in the spirit of this Mercury project, this type, the structure of the project itself is obviously enabling and promoting the collaboration between the different work package team members, and I think this is helping to create better professionals for the future. So I think this is my last slide, so I hope I was on time, almost.
Yeah, thank you very much, Lorenzo, for a very well-timed and captivating presentation. I hope that all of us will agree with me that also progress of this work package indicates very promising results. So I'm quite curious about the work package 3. So I see that Professor Sayma is getting ready. So let me tell you that Abdulnaser Sayma is a professor of energy engineering and the executive dean of the College of Engineering, Design and Physical Sciences at Brunel University in London. His research focuses specific technologies as gas turbines and micro gas turbines, organic Rankine cycles, supercritical CO2 cycles, and high temperature industrial heat pumps. He's a co-founder, among others, obviously, and chairman of the European Microgas Turbine Forum, and also member of the board of ETN Global. So Nasser, the floor is yours. Over to you. You are still muted.
So that's the thing I missed. So I need to reshare again. Sorry.
Never mind.
Okay, we'll restart again. So go from the beginning. Thank you. Yeah, it was interesting to see the result of the slide, though, showing that the component innovations are the highest on the attendance agenda. Personally, I voted for system integration, and that probably reflects why we set up the project with more doctoral candidates working on system integration and operation. But nonetheless, I believe, of course, in the importance of the component innovations, and that's indeed my area of interest, in addition, of course, to system integration and thermodynamic cycle. So work package 3 objectives, coming directly to it, it's as the title said, is component innovations, particularly turbomachinery and heat exchangers, even though some cycles might include, of course, a pump if you have a transcritical cycle. So the obvious, of course, direction to go is to try to improve the compressors, particularly as the key enabling components of the cycle, and there is the pressure to the right level, because the performance as well is clearly dependent on the performance of the compressor. We know the compressor is the most difficult in terms of judging the operating range of the cycle. But with that as well, we need as well to look at the turbines. So the first 2 tasks looking at turbines, and primarily here we're looking at a flow path of design performance and looking at transient performance. And the reason we're focusing on off design here will become obvious when we look at the expected outcomes of the various projects. Design point, it's rather more straightforward nowadays than part load, but there is particular reasons why we're focusing off design performance, as you will see. But also heat exchangers are key enablers. We have more than one heat exchanger typically in a cycle, as you've seen from the previous presentations. And the presence of carbon dioxide with some other impurities such as water and other impurities can have a detrimental consequences on the life of the components and hence the life of the cycle. So they're as important as the turbomachinery in enabling the machine to operate safely and reliably. So what are the challenges that we're encountering? And we need really to develop suitable design and analysis tools. Most of the tools that we have in the literature over many years have focused on either steam or air. So we don't know whether these tools are adequate enough or how much modification they require to enable them to be more reliable and suitable for the design and analysis and, for that matter, optimization of turbomachinery. But also heat transfer and flow phenomena close to the critical point are of specific importance. Unlike operating with air and steam, carbon dioxide close to the critical point has particular features such as large variation of properties, steep gradients, as well as the potential for non-condensation even outside above the critical point, and we call that non-equilibrium condensation due to the operational range. So we need to understand this phenomena, two-phase flow resulting from some condensation. Sometimes you may want to operate slightly subcritical cycle as well, so condensation exists there. And in regards to, of course, heat exchanges particularly, but also turbomachinery, there are transients that can affect whether we are in rotating frame of reference or stationary, that can affect the gas dynamics, and I call it gas dynamics. A lot of people using aerodynamics from the inheritance of air. Thermal and mechanical behavior are all essential to address for both turbomachinery and heat exchangers. So what we expect out of this project, we are interested in having, by the end of this project, advanced validated design analysis tools. And validation is key here. It's one of the challenges for carbon dioxide here is to find enough experimental data or other means of validating the models. So we need these validated tools for the key system components. We need to have as well, not just tools, but we need to use these tools to improve our understanding, both of design and of design performance, and that improved understanding allows us to develop methods for the design of better components, more efficient components with operating range that suits the operational requirements for modern day and future machines. But also we need to understand the flow behavior and design requirements for sCO2 heat exchangers. And that's really the main or the key outcomes of this work package. And for this to be effectively done, we have actually decided to have 4 doctoral candidates on this project. On this part, the 3 of them working on the turbomachinery and 2 working on the heat exchangers. So Mohammed, that's doctoral candidate number 9, working at Brunel, University of London, with some help from Software Way. For a particular reason that we don't have secondments because of contractual reasons of when the project was set up. And Mohammed is responsible to conduct fundamental studies to enhance off-design performance of megawatt scale sCO2 compressors. I should say actually with megawatt scale is a wide range. We are interested in hundreds of megawatt scale really, and I'll explain that a little bit as we go along. Similarly, second Mohammed Norman Salim, who is working at Politecnico di Milano. His focus is on similar scale sCO2 turbines. It was mentioned previously that we have the Scrubers project where we worked on the design of 100 plus megawatt scale axial flow turbine. And here the work is focusing on actually trying to understand the flow path and particularly focusing on the off-design performance. And then I'll jump to the last one because it's again, sorry, I think we'll the order come back as I wanted. The University of Seville is Adonis, who's again turbomachinery. He's looking at turbine designs for enhanced flexibility, again, of large scale and hundreds of megawatt scale as CO2 axial turbines. And again, we'll talk about the importance of this. So you can see there's a close link between DC-10 and DC-17, but also compressor and turbine and link typically on the same shaft. So there's an interesting here synergy between the work done in the three doctoral candidates' work. The two remaining ones are focusing, and they're based in University of Stuttgart, and they're capitalizing on the presence of significant test facilities, as heat exchanger research is more of empirical or experimental than modeling, although modeling is an important aspect of it. So Davida will be focusing on fundamental study of pseudo-condensation in the header of the supercritical CO2 turbine heat exchanger. And Ahmed Ali Weiss would be looking at the numerical investigation of the mixing of the header of the CO2 heat exchanger. And as you can see, these universities have collaboration, or the candidates will spend time in industries. Mohammed will spend time on Baker Hughes. Adonis will spend time on Siemens Energy. Davida will be looking at in Technias Rijudas SA, and Ahmed in Fives Cryo. Okay, so let's look at each project and what the objective. So I have one slide for each project, just to make up for the time taken by the other presenters. So Mohammed is looking at the axial flow turbines, hundreds of megawatt scale. You might ask why we're looking at this. A lot of the literature actually shows so many studies about radial centrifugal compressors. That's because of in the range of operation, it's much wider in terms of power output because of the low volumetric flow of carbon dioxide as being a very high density fluid. But for typically, I mean, the compressor selection, it's dependent really on the volumetric flow, but we know in the range of 100 of megawatt and above, you're most likely to need axial flow compressor, even though you might have more centrifugal compressor in there. So we did not find any significant tools for the design or even off design of axial flow compressors. And hence why this is one of the objectives. And then we're looking at the strategies to enhance off-design performance. So the research gaps identified is the limited experimental data that we need for validation, but also there are many modeling and simulation challenges. As I mentioned earlier, most of the tools have been developed for either steam or air. This project is in the early days, so the progress so far has been on development of some designs using the software AXstream provided by our partner in this project, Softenway. And we are looking as well at the development of streamlined curvature through flow models for sCO2, which do not exist at the moment in the literature, with the help of Cranfield University. And on the right here, you see some of the preliminary results of creating a characteristic map at design and off design for a single operating speed for a multi-stage axial compressor. For the Noman Salim, he's been looking at his objectives at the optimization of the turbine flow path with the objective of optimizing performance, and particularly having a better understanding of the secondary flow losses. As we know, in terms of identified research gap, because of the aspect ratio of the turbine and the size, they are an order of magnitude smaller than conventional steam turbines. Hence, the influence of the boundary layers is much more significant. But again, the same problem arises again, is the lack of experimental data for validation. So the progress so far in this area, there have been some comparison of the flow path using some high fidelity and low fidelity modeling tools, mean line design versus CFD, and initial looking at the secondary flow aspects in the axial turbine. But also there's some work on the design of seals to prevent leakage. And on the right is some of the preliminary results on both the mean line tools as well as some of the CFD investigations. Again, this one is still early stages. The next doctoral candidate project looks at, again, turbines, but here we're looking at innovative turbine designs to enhance off-design performance, because we know most machines nowadays require to be operating at a wide range of operation because of potentially backup for intermittent renewables. So the research gaps identified have been the increased need for flexible operation, as well as there's lack of knowledge in understanding of part load phenomena and identifying how to increase the turn down ratio. So far has been turbine mainline design work and validation of the numerical tool that are going to be used, but also understanding of the windage effect of analysis. And to the right, you can see some of the characteristic maps obtained. The remaining two projects are on heat exchangers, and they are both early stages because of the latest start of the candidates. So at the moment, there is an identification of motivations and objectives, which are basically experimental investigation with assisted numerical modeling of in this particular case, pseudo condensation, and then optimization of the heat exchanger design. The experiments will be done using the well-known Scarlet test rig that exists at the University of Stuttgart. And the objective, of course, is to improve the fundamental understanding and then identify what is needed to improve the design of the tools. The second PhD, the focus of it here is to understand the flow in the header of the heat exchanger, where there's a potential condensation happening. And again, this is early stages of the project, although some progress have been happening in terms of doing some numerical or CFD analysis to help in the design of the experiments, and also this to optimize the distributor of the header and looking at different header configuration, and eventually the header will be tested and looking as well in terms of flow, but also fatigue testing. And as these all early days, so we have not yet progressed in these areas in terms of like other work packages in terms of publications, and maybe it's not fair to start drawing conclusions. I mean, conclusions we draw it once we have done some more work. And with this, I hand back to Jitka.
Thank you very much, Nasser, for this very clear presentation and for great timing. Thank you so much. So there is one more presentation that we still have planned. So it's my pleasure to invite Professor Fatima Montemor. She's a full professor at Tecnico Lisbon at the Department of Chemical Engineering, and her scientific activity focuses on new functional coatings for advanced surface protection and novel solutions for energy conversion and storage. She co-authored 20 book chapters and about 300 scientific papers, has coordinated many national and international projects, and leads a team of approximately 20 PhD postdocs and young researchers. So Fatima, it's my pleasure to hand you the mic. You are still muted. Yeah.
Thank you so much. Thank you so much for your kind introduction. Thank you for inviting me for this very interesting event. I hope you can see my presentation, right? Yep.
Yes.
Okay, perfect. Thank you. So it's my pleasure to introduce you all the work that we.
Fatima, you are muted.
Sorry.
Yes.
It's a pleasure to introduce you all the work that we are developing in the frame of the work package number 4 of the ISOP project. The title of this work package, as already introduced, is Materials and Manufacturing. And, sorry. Well, what are the main objectives of this work package? Well, the main objectives are to develop advanced modeling and experimental methods to support the selection of materials, coatings, and also to understand how different manufacturing technologies can contribute to reliable and safer operations of key components in supercritical CO2 applications. So within this work package, we cover different important aspects. We aim to advance modeling techniques, especially applied to heat exchangers. We want to test and create knowledge on materials and coatings, so metals and coatings. We want to understand their durability, and we want to support the selection of the most of the materials that are more appropriate for supercritical CO2 applications. We also wanted to propose new materials produced by new manufacturing techniques, such as, for example, additive manufacturing, and understand how these materials behave in the different conditions that we can find in supercritical CO2 facilities. And we also aim at understanding the degradation of polymers in these facilities. So a very comprehensive work package addressing many different challenges. And why there are so many challenges in supercritical CO2 systems like the ones addressed in this project? First, because we can find a wide range of operating temperatures. Well, easily we can go from room temperature up to 700 degrees, and we are also we also find a wide range of pressure. And so the components and the machinery and all the equipment is submitted to very aggressive conditions. Also, we have to deal with very different exposure media, very oxidizing environments. We have to deal with cold and hot water, steam, presence of different contaminants such as H2S, etc. So the environment is really, really harsh, and this affects, of course, the durability of the components and the health and the conditions of all the equipment. So in these facilities, many different materials can be used, and often we need to combine different materials, and the combination of different materials in very harsh environments and in very harsh conditions often leads to very unexpected surprises. So I would like just to say that, for example, corrosion-related expenditures in Europe represent around 3% of the European GDP. So we are speaking about something that affects all the equipments, all the parts, and all the components in many different industries, and supercritical CO2 related facilities do not escape from this problem. So these are the challenges. And what do we expect from the work that is being done in this work package? So we want to understand, we want to have a better view on the performance of different materials in medium to high temperature ranges, the ones that we are expected to find in these specific applications. We want to understand and want to measure the corrosion rates, disfoliation rates, and their mechanisms. We want to understand the formation of oxide scales, especially when and how the contaminants that we may find in the media, how they do affect all the durability and the behavior of the different materials. It's important to understand the onset of corrosion and other aging mechanisms. It's important to develop coatings and fillers to mitigate supercritical CO2 uptake and, of course, degradation of the coated components. To understand how coatings and polymers fail, we have to understand how the process initiates and how it grows. It's, of course, very important to develop and adapt monitoring techniques. It's really important to introduce alternative fabrication procedures and materials produced by new methodologies such as additive manufacturing and understand how these materials behave in the system. And it's also, of course, necessary to produce guidelines regarding materials for different ranges of pressure and temperature. So these are some of the expected outcomes. They aim to fill the gaps that have been identified in this field and that are well reported in literature. Contributing to solve, to fulfill these gaps and to solve these challenges that I identified before, we have three students, three young researchers working in the project. We have Mahira Akhtar. Her topic deals with coatings. Especially, she will be focusing the study of different polymeric components and coated steel parts. And she will study the behavior of these materials. Then we have Jules. Jules is dealing with the durability and corrosion phenomena in different metals and alloys. And we have Mohamed, is more focused on heat exchangers and is addressing additive manufacturing technologies for heat exchangers. Mahir and Jules are based in Tecnico in Lisbon, and Mohamed Khaled is based at University of Stuttgart. And they will be collaborating with different industrial partners that are very important contributors for these work programs. So in terms of timeline, I will not repeat what was said before. So these students start their works November, December 23, and they are expected to finish by December 2026. And we want really to advance knowledge on metals and superalloys and also in polymers and additive manufacturing technologies. So going a bit more in detail on the working programs. In what concerns advancing the durability of polymeric coated parts, there are some important outcomes to be considered. So the durability of polymeric and coated parts in supercritical CO2 applications is of major concern. There are many components that have to be painted for improving their lifetime, of course, but high temperature and high pressures in the presence of moisture and contaminants induces severe damages. Corrosion is, of course, a major cause of failure in these parts, and we do need to have a better view and understand better what are the degradation mechanisms and the durability of these components. Therefore, the expected outcomes are related to the understanding of the durability and the mechanism of failure of polymeric components used in supercritical CO2 facilities. Also in this work, we aim at developing polymers with increased lifetime, namely polymers that can somehow heal themselves under the presence of aggressive conditions. It's also an objective of this work to understand, to apply non-destructive evaluation techniques and allow them to be used to understand the durability of the materials. And finally, it's also important to understand how additive manufacturing technologies can contribute to develop better materials and materials more durable for these applications. So far, the work led to the identification of a specific coating that is expected to have a very good durability at high temperatures. This coating material is now under test, and different corrosion inhibitor pigments have been developed, and the work has been disseminated in national events, and in the future it is planned to disseminate to work in international conferences. The work that is being developed by the candidate Jules Ahabi, it aims at advancing the durability of corrosion-resistant alloys. He has selected different metals that are usually found in different components and different parts. Of course, the use and the selection of the material requires a lot of care, and it's very important to understand which material is more appropriate for a specific environment. And therefore, it's extremely important to understand the implications of extreme operating conditions on the corrosion resistance of different metals, and to develop advanced modeling and experimental methods that support better selection of metallic materials. Finally, the candidate Mohamed Khaled is addressing additive manufacturing technologies for heat exchanger applications in supercritical CO2 power systems. So he's evaluating different design methodologies and optimizing the geometry of an intended prototype that is designed and conceived for enhanced durability and performance in supercritical CO2 power system. So we're also investigating different alloys to address and to understand its processability, and studying and optimizing the additive manufacturing process, the intended application. Of course, it's important to characterize the materials that are used, and to investigate all the steps that are involved in the fabrication of the components. And with that, we expect to be able to print a small-scale prototype using additive manufacturing, and to propose different recommendations for designer and manufacturers. So a very ambitious work plan that I am sure that will be running very well in the near future. And finally, this work package has strong interaction with the work packages that have been previously presented, namely with systems integration, operation and control, and with work package number 3, in which we address new innovations in different components. So that's all. Thank you very much.
Well, thank you very much, Fatima, for the great overview and for sharing your expertise. And this is it now. All the speakers have already delivered their presentation. So now it's almost the time for the Q&A. However, before we do this, not surprisingly, we have another Slido, because that's something I've already announced before. So take again your phones. If you haven't closed the session from before, it should still be working. If not, then you will need to rescan the QR code. So let me put it in the presentation mode so that you can see the QR code. Can you see well the QR code? Okay.
Yes.
So the last question is, surprise, surprise. It's exactly the same like the first one. So after hearing all the 4 presentations, we wanted to check with you if you have maybe changed your mind. So please vote exactly on the same questions like before. So I think that we are the percentages are almost fixed. So I will ask again David to debrief. David, for your information, I have taken note of the first Slido, and obviously you know that it was the components innovations that were the first one. So now we have 33%. Before we have 42. The second one was system operation with 37%. Now it's 42. Then we had materials with 12. We are still at 12%. System integration with 7. Now we have 9, and other also 2%. So there is still a little bit of difference. So what do you think about it, David?
That was probably to be expected. I think that the most significant change is now system operation, transit performance, and control leading our interest with a large enough gap, I would say, so as to think that this is not only out of the difference in the number of participants. So I think we had probably like 54 or even close to 60 answers for the first Slido, and now we have fewer people answering. And then system integration has come back a little bit. So I after having worked on the technology for the last 10 to 15 years, I still think that there are many open questions regarding system integration. So of course we understand that the first two are probably capturing most of our attention, but then at the end of the day, it's also true that the components are inserted into the system. So system integration is about how you put them together. And then also the first one, system operation, is about how you operate the whole thing. So the system integration is again, as I said in the first slide, though, a cross-cutting topic, which is present in all the different categories. We'll see. When we complete the project in a couple of years, it will still think the same based on the results.
Thank you, David, very much for your thoughts. So that was the last thing from us, and now I'm quite happy to open the Q&A session. So I will invite all the speakers and also the moderators, Giovanni and Mohamed, to join me on the stage. I'll stop sharing my screen, and what I'm going to do next is that I will let all of you to switch on your mics and cameras so that you can just raise your hand or you can directly start talking.
I think, can you hear me, right?
Yes.
Yes, John.
Yes. Okay. Hello, everyone. I'm Giovanni Lopez, and jointly with my colleague Mohamed, we will moderate this Q&A session. So I think we have a couple of questions already in the chat, and yeah.
Okay, great.
Mohamed.
Let's start with those.
Yes. So first one was direct related to work package 3. Is in perspective to your work on actual turbine design. Do you have any work on 1D mean line design of steam turbine? What are the key differences between modeling of sCO2 axial turbine compared to steam turbine? I think this is for work package 3 and exactly for people that is working with turbines.
Yeah, I can try to answer that. I actually, my previous work was primarily on gas turbines, air turbines, rather than steam turbines. I did not do any work on steam turbines. So, but to answer your question, I mean, from what Giacomo have put in, well, not yet, but his team on their presentation, there's an order of magnitude difference in terms of the aspect ratio of the blades in supercritical CO2 compressors and turbines compared to steam turbines. And the reasons behind that, of course, is the high density of the supercritical CO2. And that would have profound impact on the proportion of the flow path or the boundary layer as part of the flow path. Means that the flow is dominated by a boundary layer. which make a significant difference in the proportion of impact of the various loss mechanisms. So when and we know that most of the one-dimensional design tools have been developed based on empirical correlation related to experimental data or practical experience. And what we notice is that some of the existing models probably applicable that are used for air turbines and steam turbines, but they need probably some adjustment to certain coefficients to take into account the significant importance of the boundary layer influence on the flow behavior.
If I can add to that, there is one side of it, which is understanding the impact of the tools that we are using on how much we can estimate the performance of the turbine based on different working fluid that we are using. But then on the other hand, what we're also doing within the project is looking into operational flexibility. And that involves mostly two different aspects. The first one of which is turn down capabilities, and you said that last year during your presentation. We have one researcher working on that and to understand the operating range of the system. And then we're also interested into the dynamics of the turbine. So how fast can we start the system up? Mostly looking into whether or not this technology can deliver balancing surfaces to the grid. And that is looked into not only in the work package working on the components, but also in work package 2 working on system dynamics. So it is a portfolio of research topics that we are working with.
So if I can finally add something on it, what was said by Nasser and David is totally true. And if I can add something more, we need to consider also that due to the characteristic of sCO2, we have an important sealing that you have to consider, let's say, in the cavities or at the tip of the blades, that is, let's say, somehow similar to what happens in very high pressure part of the steam turbine, but this is some kind of super high pressure steam turbine. So everything that, all the difficulties that maybe have been studied in the high pressure turbines, that could be steam turbines, that could be secondary flows, leakages, seals, now are magnified. And so probably are beyond the level and the limits within that the correlations were and the knowledge was developed. So the research must be focused on these aspects that eventually become important to define the performance of the machine. But also, for example, the loss on the valves upstream of the machine is much more important for sCO2 turbines than for steam. And also these things must be considered. So you must consider the turbine and what is around it.
Yeah, thank you very much for your answers. And actually, this question had a second part, but I think you already covered and answered it. And it's how the experience of steam turbines can help in the design of CO2 turbines. So I don't know if maybe you want to elaborate more, but I think you already gave some insights into this.
I think that the starting point is the high pressure part of the turbine, of the steam turbine, but still going beyond that. So can be used as a starting point, and then going ahead with high fidelity models of all the important parts, flow path, secondary system seals, flow in the windage, and so this is the starting point. But we need to go beyond the boundaries of the knowledge about that.
May I as well contribute a little bit to that? Our findings from a previous project, we actually initially thought prior to starting the project that would be similarity between a design of a steam turbine and a design of a supercritical CO2 turbine, and just a scaling down. What we realized actually is not that straightforward. Because of the bending stresses on the blades are completely different. And then the optimal between the number of stages versus stage loading is a completely different. So really the fundamental knowledge is there, but actually the design can be completely take a completely different direction in the turbine. So it's a very interesting findings. There are a number of papers that we have published, if you look them up, are resulting from the Scarabæus project, which shows quite the various aspects of the a large scale, we're talking here, multi-stage axial flow turbine. It's combined with you have to take into account both mechanical design or mechanical features as well as the gas dynamics. I'll keep shifting rather than aerodynamics, what people use, and that I'm not sure I can map out the same experience, but the knowledge, of course, is important, but it won't be a scaling, if you like, or dynamic scaling of a turbine from a size, from a fluid to another, from a size to another. It's not as straightforward.
Thank you so much, Professor. Let's go to some other questions that were received in the chat. The first one is a technical question directed to Work Package 1. If anyone in Work Package 1 or maybe the Work Package leader can answer this question. It's regarding the directly fired oxycombustion sCO2 power cycles. The question says that one of the key challenges in the directly fired oxycombustion sCO2 power cycle is the high energy consumption of air separation of the air separation unit, the ASU. Have you explored any alternative oxygen production methods that could reduce the energy intensity compared to the conventional cryogenic separation? Thank you.
I think Giovanni, if you want.
Yeah. I think I'm the one for for this. Yeah, the short answer is yes. Actually, if we remember the presentation from Giacomo, there is a chart there where we can observe which is the most suitable oxygen production method according to purity and mass flow that we want to produce. So the answer is yes, but with the current technologies, we are still needing to use the cryogenic just because of purity and because of the mass flow that we need to for operating the power cycle at megawatts, or let's say hundreds of megawatts scale. So yeah, there are some emerging technologies that are being developed, but they are not totally commercial. For example, just like chemical looping or ion transfer membranes, etc. But as we are, or in the situation that we are right now, we have to still rely on cryogenic.
Thank you so much, Giovanni.
Maybe I can add to that. I'm now changing hat and speaking as the supervisor of design statistics. And one of the aspects that you are looking into, Giovanni, but maybe you can comment on that, is using the air separation unit more actively, let's say. So one would think, well, I'm producing oxygen and don't really know what to do with the nitrogen that I also by producing, and then the oxygen I burn it, or I'm using it to burn fuel in the Adam cycle or whatever cycle you use. But you are actually exploring avenues to have them decoupled and used more actively. And I mean, you don't really have to give details probably about what you have in mind yet, because you still have to work about. And but I think that is an interesting approach to the combination of the air separation unit and power cycle. What do you think?
Yes, actually, this is an interesting path for research. And yeah, basically the idea is that under the current conditions of the electricity market, we can think about this air separation unit as a more active component of the cycle, and we can actually take advantage of the nitrogen, because current applications are not taking advantage of nitrogen, at least not for power, for producing the power in the plant. So yeah, it's basically just a bit playing with the current market conditions and how can we deal with that, and how can we operate our system, both air separation unit and the power block.
Thank you, Giovanni. Let's also take a chance if anyone in the audience would like to ask a question now. We would like to address all the questions that you want to answer, that you want to ask. If you want to turn on your mics, your cameras, or even if you want to write in the chat or you want to write in the Q&A part. Okay.
You have a new question on the chat.
Yeah, we have a new question. Yes. Could you please, I think this question is directed towards me and my professor. Yeah. So I can read it and answer it maybe. Could you please comment on the usage of axial compressor near CO2 critical point for hundreds of megawatts scale plant? They were also mentioning of a compressor sharing the same shaft with the turbine during the talk for 100 megawatt scale plant. What benefits the axial compressor offer whilst potentially reducing the plant turn down, operational flexibility when the axial compressor with fixed speed is used, likely inlet guide vanes or recirculation? The second question is the efficiency gain by using axial compressor notable to offset this at a large scale? Wow, it's a three-part question. And the third one is high efficiency plant beneficial over high turn down plant, particularly in the future energy scenario with large penetration of renewable energy to the grid? Okay, regarding the axial compressor, first of all, near the critical point, we might have lots of challenges in predicting the performance. Actually, we do have lots of challenges in predicting the performance of the axial compressor, and lots of challenges in predicting the off-design performance of the axial compressor. And this is going to be the bulk of the research, because we might deal with because the fluid density and the volume flow rate is going to be very the fluid density is going to be very different from the ideal gas-based models. So we're going to work a lot on adapting loss models on adapting loss models that take into consideration the sharp changes in the thermodynamic properties of CO2. The compressor sharing the shaft with regards to the compressor sharing the shaft with the turbine. This is not something that was decided per se. It's not something that is written that's set in stone. We don't have a vision for the whole. We don't have a vision for a whole plant currently. We're working on separate components that share boundary conditions, and we share cycle configurations. As for the first part of the question, the benefits of the axial compressors while reducing the plant turn down, the axial compressor will reduce the size of the carbon dioxide being used, the supercritical carbon dioxide being used in the design of the turbo machinery reduces the size of the turbo machinery itself. So it also reduces the size of the plant. Using the IGV, the inlet guide vanes, is used as a control method. It's also proposed to be used as a control method. This would be a collaboration between myself and the other researcher, Leo, to monitor the dynamic, the surge of the compressor, and to monitor the dynamic response. The efficiency gain by using axial compressor is notable to offset this at a large scale. The efficiency, if compared to radial turbo machinery, if compared to radial compressor, yes, the efficiency gain is going to be significant, which is one of the things that we will be exploring. As Professor Sayma mentioned, there isn't much experimental data on axial compressor, on sCO2 axial compressors. The research is currently being developed. There are some research papers that compared the efficiency and the efficiency and the performance of centrifugal versus axial compressors using a preliminary mean-line design tool and a mean-line performance analysis tool for the same power input, for the same mass flow rate, volumetric flow rate. The axial compressor produced was much more efficient, and it was the other word, more efficient and more, I'm sorry, I don't remember the word. Yeah, it just skipped my mind. Is high efficiency plant beneficial over high turn down plant? I'm not sure I understand what a high turn down plant is. If Nasser or David can assist us in answering this part of the question.
Yeah, thank you, Mohammed. I mean, this is good. So let me just add a couple of more points to what Mohammed said. The choice actually of axial compressor is not a choice, although it's important because it's higher efficiency than centrifugal. But this is not really the key reason for the choice of axial compressor. The choice happens because there is a certain volumetric flow at large scale where it's no longer feasible to use centrifugal compressor. And that happens. I mean, there is no really specific power output range that we can decide when we use, because it only depends on the cycle configuration, the pressure ratio, whether using one compressor or two compressors, whether it's a pre-compression cycle or recompression cycle. But the common, although it's not really, don't put that in set stone, the common knowledge is if you go to about 50, maybe 70, 80 megawatt power output, depending on, as I said, all these parameters, you probably most likely are forced to go to the axial flow compressor because the centrifugal compressor is no longer feasible. And now going to your question, is efficiency because it's a single shaft compensated by the fact that it's a single shaft? Of course, on a single shaft, most large-scale machines, well, all large-scale machines for mechanical and economic reasons are on a single shaft, and they probably operate at synchronous speed, either 3,000 RPM or 3,600 RPM. So there is inevitably a compromise here that need to be found, and that need to go through optimization between the design of the compressor and the design of the turbine to achieve, of course, the highest performance of the entire plant rather than the particular component. It's the same philosophy I use in the design of gas turbines, so there's no different from that choice. But I agree with you that the use of IGV is instrumental in terms of, compared to centrifugal compressor, in terms of helping the off-design performance and allowing a better turn-down ratio. Just to clarify, the turn-down ratio is how much you can actually, the ratio between the lowest, if you like, power output that you can to the design point. So how much you can turn it down while still operational, and that is important for operational flexibility when you're using this machine, either as a load following or to provide a backup for intermittent renewables. Then you need really to have as high flexibility as possible. In my view, and I think David would agree with me, but I'll leave you to say that, as we go forward with more and more integration with renewables, but also modern energy systems, which are rely a lot in integrating centralized and decentralized systems. You need to have as flexible as possible as operational flexibility. You would want actually to have high performance across the board, not just at part load, at design point and part load. Of course, there is a compromise to be reached here. So your optimal will be on a typical operational seasonal envelope, really. So maybe David, you want to add?
Well, yeah, no, I agree. I mean, there is one additional element probably that we are looking into, which is the the impact that the turn down capability or ratio has on the operating and maintenance cost. So the reason why we want to take the system as low load as possible, which is, you know, increasing the turn down capability of the turbine, is just to avoid having to shut it down. Let's say for just a few hours, because we are just not making money in the market. Because when we have to shut it down and then start it up, it is a massive casing, it is a massive shaft. You have to heat it up, and then maybe you cannot be as fast as you would like to, just to come back online and start making money again. So what we are looking into, in particular, in our researcher number 2 on GAD, is looking into these trade-offs. So how much money I make, how much money I lose if I have to shut down and start up again, against how much money I lose because I keep it spinning, even if a low load and low performance. So the answer that I would probably have for that question is there is no answer for the question unless you incorporate the features of the end user. What is your heat source, your energy supply? What is the business you're interested in? Depending on that, you may go for the more flexible, less performant option of the centrifugal compressor, or maybe the opposite.
Okay,
Thank you so much.
So if I can add one point very quickly, from the technology side, this kind of axial compressor could be very, very useful for energy storage based on sCO2, because in this case, there is a charging cycle that needs to have a high power compressor. And if you think to a large scale energy storage, this compressor will be the key component of the system. And to be high efficiency with an axial flow machine could be very useful.
Good. I think we have one probably very fast question to conclude with about dry gas seals. Maybe Lorenzo, you want to take this one? There is one question regarding.
Yeah, I've seen it. Yeah, I think the dry gas seals for the closed cycles, so all these externally heated, are still considered needed in for both compressors and turbines. I think there is a good development on the. I mean, compressors dry gas seals are a standard in the industry in the temperature range in which will be used also for the supercritical CO2 cycles. For the turbine, there is this technology step of cooling the dry gas seals, or the other technology development path is to develop dry gas seals which are capable of running at high temperature. And this is a path that is being followed by one of the major dry gas seal suppliers. There are publications available, and so I think the considering the overall effort of the industry and the research, this capability of using dry gas seals at high temperature will become more and more standard. And in the directly fired cycles, since there is a continuous addition of CO2 through the combustion, there is less this need of dry gas seal on the hot machine. So there it becomes more a matter of optimization of the efficiency of the cycle. So I hope I've answered the question.
Thank you so much, Lorenzo. Yitka, do we have any time for more questions?
Well, the time's up. It's already 4 o'clock. I'm not sure. Are there any other questions that need immediate answer?
No. If anybody wants to raise a question, we could answer, but I think the time is up. So.
Well, in any case, you will receive the proceedings of this session in a form of a presentation, and each presenter put his email coordinates at the end. And obviously, you also have you had just now all the contact details for the ISO project, including David Sanchez, of course. You have my email address as well. So if you have still questions, you can still address them to us, and we'll make sure that no question will remain unanswered. But if there is no question at the moment, and obviously the time has already run up, I would like to thank in particular to all the speakers for making themselves available. It's not a matter, of course, to gather so many high-profile people to make sure that they have the time at this particular hour. So thank you so much. Also to all the young researchers who put lots of effort in preparation of the session. Obviously, all the thanks of us go also to you, the participants, for attending, for your loyalty, and for engaging with us in forms of Slido and questions. And obviously also to the people that are not on the stage, but who are greatly supporting every single time these webinars. In particular, my colleagues from the sCO2 working group. We very much hope that we will see you next time. We are not sure exactly when the next time will be, because we are still preparing the next session. When we will know what exactly the date will be, the topic and the speakers, we will obviously let you know, as we always do. And you will receive the proceedings for a presentation and the video recording also in a few days. I will send you an email with the link so that you can have a look and share it with whoever is interested. And with this, I can call it a day. So have a nice rest of the afternoon, and see you next time.
Thank you.
Thank you.
Goodbye.
Bye.
Thank you very much.
Bye-bye.
Bye-bye.